Hello and welcome to our second episode in our student speaker series. I'm Yasser Qureshi, the Outreach and Talks Officer. We have three speakers this evening, bringing their insight into some very interesting topics. Firstly, we have Patrick Fahy. He is a fourth year maths student who's discussing how he uses neural networks to solve differential equations. Then we have Janique Krasnowska, apologies if I pronounced that wrong, final year maths and stats graduate student who's going to talk about her experiences at Parexel, where she encountered non-parametric equations. Lastly, Harry Fallows. He's a fourth year computer science student, and he'll be talking about his third year project on generating graded sight reading music using neural networks. Quite a mouthful just then. Our speaker socials will be in the description, and with that, I'll now pass it on to Patrick.
Okay, well, hello everyone. Welcome to my talk. I'm going to be talking about neural networks applied to differential equations, well, in particular PDEs, so some lovely maths and data science in there as well. In addition to what Yasser said, I'm also the maths and stats ambassador this year, so I'm the one making the examples for the maths and stats beginner course for Python. Okay, so next slide, please. So what I'm going to look at, I'm quickly going to define the PD I'm going to look at, and then quickly introduce neural networks for anyone who hasn't seen them before. And then hopefully I can use a neural network to solve the problem well. Next slide, please. So just to give a bit background on the PDE. So if we assume we have a rod, which is very, very, very thin, that just means I'm considering it with no width, just one dimensional. If we have a length n, L, which I'll take as 1, we want to see how the temperature varies of this solid over time with an initial temperature function, as you can see, f of x. And we can find that the heat satisfies this heat equation you can see at the bottom. And you may see that usually there's a constant in front of the second order term, but that's basically just, I'm just assuming certain properties of the solid that makes it a nice constant. That's one. Okay, next slide, please. Okay, so now I'm just going to give a quick background on neural networks, just for anyone who hasn't seen them before. I'm sure a lot of you have seen them before, so I'll just do it quickly. Okay, next slide, please. So here's kind of a basic neural network. You see the input layer, and what the input layer is basically the dimension of your input. So we have 3 different features, for example. There's 3 different nodes, which is what the circle is called, that gets inputted to the neural networks, and the output you see is 2-dimensional here, so we get 2 outputs from it. And the hidden layer, you can have multiple hidden layers. What this does is you specify an amount of nodes, and the arrows kind of show a relationship between the layers. You calculate some function of the input layer and take that to the hidden layer and then to the output layer, which is shown on the next slide, please. So here we see quickly how everything's calculated in the node. We take, for example, 2 inputs, x1 and x2, and calculate a weighted sum of them plus a bias, and then use an activation function, which is what f's called in this instance, to calculate an output from the node. Yeah, that's really what happens in each neuron. So next slide, please. So how do we train them? And I found myself too funny not to include a picture of a train. So basically what we do is we define a loss function, which is kind of like how wrong our output is, so we compare that to what it should be. Then to train it, we initialize some weights and biases, which is quite a big problem actually, and provided a link there which you can go to. And basically what we do is take input data and then calculate the output given the weights and see how different that is to what we want. And there's something called backpropagation, which it looks absolutely disgusting the first time you see it, but it's basically just a simplification channel to update the weights to make the model closer to what we want. So that's kind of a quick background on neural networks. So now we'll go back to the PDE problem. So next slide, please. So here we have our problem, the PDE with our initial condition as before. And if we assume F takes this form, and we have initial conditions at each of the boundaries, so we have specific temperatures on each corner of the rod, then we can see if we can study how the distribution of temperature flows throughout time. So next slide, please. Okay, so the first bit we need to worry about is first getting the data we need to use to train our model. So there's different parts to our neural network, as in we need it to satisfy the PDE we had before, and that's on the whole domain. So we create data, as you can see, the X, R, I, and T, R, I, just to cover the domain. Then we also have the initial condition and boundary condition. The initial condition being the initial distribution of heat, then the boundary conditions at the ends of the rod. So we create data for each of those, as you can see. Next slide, please. So this is where it really gets tricky with a lot of applications of neural networks. You'll just have a simple loss function, which, for example, can take the mean square error of your predictions of your neural networks. But with this, we have different components. We have our PDE that we need to worry about, and we have the initial and boundary conditions. So the first loss function you can see, I've defined basically the error in the PDE, and that's off of the main boundary data that we created in the last slide. And then similarly, for the initial condition, the second loss function, we can see the error of our approximation with what we should have it, as well as the boundary conditions in the last one. So then we can define our main loss function as the sum of these three. Or you could weight these differently to give for one part more preference if it's quite important for you to get it right. So yeah, next slide, please. So now we'll get on to talking about how we train the model and to see what kind of results we get. Next slide, please. So to those of you who haven't looked at neural networks much, this might not mean that much to you, but our hidden layer structure is just 50, 75, 50. So that's the layers in between the input and output layers, and we use an Adam optimizer, which is basically like an improved version of stochastic gradient descent. But I won't go into that too much because that's quite complicated. And I trained it on 200,000 iterations, which it's quite a lot, but I think I kind of trained it for probably about 50 times longer than I needed to, just to get it ever so slightly better than it was previously. So next slide, please. Let's now actually look at the results I got from this neural network and see if it was very good. So next slide, please. So this is the plot of the loss function over time that I got. And I actually removed the first 300 iterations because the loss function really reduces a lot in the first few iterations. So it would just be a vertical line down and then horizontal line, so it wouldn't tell you much. But it shows that the training gradually decreased over time, so it looks like it did what we want it to, at least. Next slide, please. So here we see that actually it was quite a good approximation. We have our exact solution on the left and what we wanted to get in the middle, and they're practically identical. The largest absolute error was approximately 0.0003, which, well, physicists would say they're the same thing, so it's good enough for me. So it was quite successful. The model only took about half an hour to train, but I trained it a simpler one in about a minute, and it was practically as good. But one thing to consider is the fact that it is quite a simple PDE. So as these things get more advanced, you'll need more data and maybe more intricate data to generate a distribution in certain areas where the solution does fluctuate a lot. And yeah, well, thank you everyone for watching. If you go to the next slide, please. If you do want to see the code behind this, there's a lot of TensorFlow. Because the loss function is very awkward, I wasn't able to use Kira's, which is very sad. But you can see a lot of nice low-level TensorFlow code if you go to my GitHub and have a look. Yeah, well, thank you very much. If you've got any questions.
Okay, hello, I'm Janique. I'm going to be talking about non-parametric statistics, and I'm going to start by introducing myself because this is quite important for how this presentation came about. So this July, I finished 3 years of a math sense degree, and this July I started working for a company that analyzes clinical trials called PowerExcel, and I started programming a lot of tables and listings, and I encountered a lot of methods that I've never seen before. And after doing some initial research, I learned that they all belong to one family called non-parametric tests or methods. And yeah, I would like to start by talking about why they're needed in while analyzing medical data. So with medical data, we often encounter quite unique distributions because the data often comes from questionnaires, so it's not continuous, it's discrete. So like, for example, we ask patients about their pain levels, so that's on a scale from 0 to 10, and it also often tends to be skewed because we only include patients above or certain threshold in the trials. So for example, patients with really low white blood cell counts or really high insulin. So that makes the data not very representative of the population and often skewed or discrete or things like that. So it doesn't follow the classic normal distribution shape that we see on the slide. So it doesn't have this nice bell curve shape that a lot of the traditional statistical methods tend to assume. So let's have a look at an example. So the first example I would like to give is a data set from the UCI machine learning repository, and it contains 100 observations, half of which are healthy patients, half of which are patients with breast cancer. And what we're going to look at is a hormone called resistin, and the name comes from resisting insulin. So it's a hormone related to diabetes, to obesity, to cholesterol levels. And we're going to compare the levels of that hormone between two groups, between healthy patients and patients with cancer, to see if there is a difference. But basically, what we do more often with clinical trials, we compare between treatment groups, but that's exactly the same method that could be easily applied to comparing between the placebo and the treatment group. So here, when we plot the data on a histogram, at first sight, they seem a bit different. We see that there is, for the controls, there is one outlier around 80, but in general, for the patients with breast cancer, the values at first sight seem to be a bit higher. But unfortunately, when we present data to regulatory authorities, we can just say, oh, the histograms look different because our drug wouldn't really get approved. So we need to come up with some formal statistical test. So some of you might have heard about the t-test because it's widely applied in social sciences and sciences. It's the classic test for comparing to independent groups. So if you want to check that two data sets or two subsets of a data set you're working with have the same distribution, you often apply a t-test. Here it's a variant of the t-test called the Welsh t-test. And what it assumes is that the t-number we calculate from it based on the mean and standard deviations follows the normal distribution for this number of patients. But what happens with this data set of resistin is that it breaks this assumption. The t-number calculated from that doesn't follow the normal distribution. So what can we do in this case? Because we still want to get our drug to market. Do we have any alternative? Yes, we do. And here is where non-parametric statistics come into play. So to understand what the idea behind non-parametric statistic is first we need to think what parametric statistics or distributions are. So with parametric statistics, we assume that a certain numerical characteristic like mean or variance describes the probability distribution well. And non-parametric statistics are the opposite. So they don't assume an underlying distribution, or they assume we don't know anything about those parameters like mean or variance. And the most basic type, and the type that the first example of non-parametric test I'm going to present belongs to, is the order statistics. So instead of relying on mean and variance, they rely on the ranks of observations. So for example, that this data point from group A is bigger than this data point from group B, or this data point from group B is smaller than this data point from group A. So they don't rely on a single number. They look more the whole of data set. Yeah. So the classic alternative, the classic non-parametric alternative to the t-test is called the Mann-Whitney test. It's also often called Wilcoxon rank sum test, but Frank Wilcoxon has a lot of tests named after him, so I don't really like to use that name because it's confusing. And what it tests is that the probability of a random sample from dataset A is bigger than a random sample from dataset B is the same both ways. So the probabilities of random numbers being bigger than each other are the same independent of which dataset they're from. So let's see how the two compare. So here it's a graph of the average p-value versus the number of patients. So here we want a low p-value because we saw that the distributions do seem to be different. So we want a low p-value. So if the line is lower on this graph, that's actually better. So here we see that the non-parametric method gives us a significant p-value much sooner, because this is the perfect situation where we should apply a non-parametric test. And that is especially important if we're working with some rare disease where we couldn't have so many patients. So would need a significant result quite quickly, and we couldn't recruit so many patients. And this is also, the non-parametric method is also doing so well here because of the outliers, that parametric tests really don't deal well with outliers. So here, it's not always the case that they're more statistically powerful. Sometimes, especially when we're dealing with nice distributions, the t-test is much more powerful. So it really depends on the case. But here, it was a really good data set to apply non-parametric methods to. I would like to talk about another situation where we apply non-parametric tests, and this is where they really shine. So this is a bit more complex. I'm going to be talking about survival data and survival data analysis, which is a bit more complicated than just comparing two datasets. Because, for example, we often deal with it. I've worked in a lot of oncology trials, so we often do survival analysis there because, unfortunately, we're still not looking for drugs that cure cancer, but we're more looking for drugs that expand the patient's life expectancy. So here we see the survival probability after heart transplant. So we see that it drops in the beginning and then levels off the more time passed. So, and we also on this graph we see crosses on that line, and what they mean is they represent something called censoring. So this is what actually makes survival analysis so complex, because imagine our trial runs for 3 years, and at the end of the trial we hopefully still have a few patients who are alive. So we can't really follow up with them until they pass away, because that may take 50 years or however many years, and that's not really practical when we have a good drug, especially a good working drug that we want to get to market. So at the end of the trial, we censor those data points. So we know they were alive at this point, but they might have died the next day, or they might have lived for 50 more years. We also have censor points when someone is what we call lost to follow-up. So they stop picking up the phone, they stop replying to us. So we know the last time we saw them, they were alive, and we don't know what happened to them. So all those crosses on this line are censor points, and they're also included in the analysis. And why we basically only use non-parametric statistics when it comes to survival data is because the mean, which is what we usually rely on with parametric statistics, doesn't give us a good picture of what's happening. Because if we imagine a surgery, so a transplant surgery, we have 10 patients, we have a surgery, 9 of them die immediately, and then 1 lives for 50 years. So the mean of that is 5 years, but you wouldn't really want to have a surgery that 90% of the time you die immediately during it. So that's why we have to more rely on the median, which is what non-parametric methods tend to do. So that's why we always consider the median when it comes to survival data. So here, what can we do with it? So we usually compare placebo and treatment groups, but here I use the same data set and I subsetted it by age of the patient. So the red line is patients under 45 years, so it's a bit higher survival probability, what we would expect for statistically younger patients. And also the blue line of patients over 45 years old, which is lower, which is lower survival probability, which is what we would probably expect for a bit older patients. But actually, when we, for example, do more things with this graph, do more analysis. For example, we can start with plotting the confidence intervals, which are the transparent regions on this graph. And what confidence intervals mean is that that line, in 90% of the cases, might have landed anywhere in those confidence intervals. So what we actually see is that those confidence intervals overlap quite a bit. And also when we do another non-parametric test, which is called the log rank test, which is the test we always do with this sort of Kaplan-Meier survival graph, we also get a p-value of 0.2, which doesn't allow us to reject the null hypothesis that those groups indeed differ. So if we were testing a drug here and one group would be placebo, one group would be the treatment, this sort of value would not allow us to get this drug approved. So this drug wouldn't have enough of a significant effect on patients to get it approved, unfortunately. So yeah, this is my last slide, and I just wanted to say that I didn't know about any of this when I started working for my company, but actually, after doing some research, I realized how useful those non-parametric methods are when dealing with very unique distributions or very unique cases, such as in like survival data analysis. And I just wanted to say that, I hope you remember about them. I hope you can, when you encounter some unique data set, that you'll remember that there is such a thing and you'll try to find a test that works in your case, because there are many of them. I just mentioned 2 in this presentation. But yeah, there are many for many different cases, comparing 2 groups, comparing 3 groups, analyzing a certain type of data. And thank you very much for your attention.
Hi, my name is Harry, and I'm a 4th year computer science student. And I'm going to be presenting my 3rd year project, my dissertation last year, which was in generating graded sight reading music using neural networks. So I think the first question to ask is, what is sight reading? So some of you might be aware of what sight reading is, others not. So it's part of a musical instrument examination, where the candidate is asked to perform a piece of music that they've never seen before. Now, depending on the examining board, it might be mandatory for you to do it in your test, or it might not be mandatory depending on the grade. And for every board, they come out with different requirements. For example, the length of the piece that's required, or the certain time signatures or key signatures, or the pitch range, for example. So the second thing to ask is, what is a neural network? I'm lucky enough that Patrick has described some of this for me already, so I don't have to go through it all again. But essentially, it is a computational model that is designed to loosely replicate the human brain. So it consists of these nodes and these edges, and it has an input and an output. And we're trying to learn something. And the way we learn things is by inputting loads of data, as well as some labels for the data. So basically saying what the output we want is, and during the training we adjust the weights of the edges, and hopefully improve how good our network is at doing what we want it to do. So the specific type of neural network that I utilize in my project is called a recurrent neural network. So recurrent neural networks are a specific type of neural network that contain these loopback connections. So in a traditional neural network, it's sort of it just propagates forwards. So that means like the input layer is connected to the layer that is following it, and then that connects the next one until it gets to the output layer. But a recurrent neural network contains these connections that go backwards. So the reason you'd want these is if you're dealing with sort of time series data. So that's data which at one point in time will influence something at a later point in time. So a good example of this is if you're trying to predict the stock market. So if you've got, say, for example, a week's worth of data on the price of a stock, perhaps you're polling it every hour, and you want to predict what happens in the next hour. Obviously, there's some correlation between each of the data points in the time series, so it's useful to have these influences in the network. And the specific type of network I use is called a long short-term memory network. It's just a type of recurrent neural network that is designed to avoid long-term dependency issues. So it's better at retaining information over a longer period of time. And this is ideal for music because music can be seen as just a time series of notes, and notes later on depend on notes that have happened previously. For example, they'll be in the same key probably. They're not going to be a massive interval apart, that sort of thing. So as I described in the stock market example, it's a load of time series data, and we're using it to predict a single piece of data, for example, the stock price in the next hour. So you might be thinking, how the hell can you generate music using this? Like, it doesn't make any sense. Surely you're just going to get a one note output, and you'd be right. So in that network instance, all it's doing is we're getting an input of music and we're predicting the next note. But how can we generate music using that? So this is what I'm calling the sliding window design of the system. So it utilizes, like the network I described, it outputs a single note. But then if we append that output note to the end of the input that we used previously, we can then predict the next note, and then the next note, and the next note, and the next note, until we get the length of piece of music that we want. And all the generated, all the predicted notes will just be appended in one long piece of music, and that'll be a piece of music. So just a quick note on the technologies that I used. So Python was the programming language I used, and that's because Python has a huge range of capabilities with regard to neural networks. It's a very quick and easy language. You don't have to think about things too much. And there's a lot of other stuff going on in the project. I didn't want to have to deal with memory allocation and stuff and using C or C++ or anything like that. And the library I used was Keras. I think Patrick mentioned it. Yeah, it's quite an easy library to use for neural networks. It's very high level. You can just say, I want this type of network, I want this many layers, I want to use this loss function, and it'll do it all for you. So that's really useful especially if you want to experiment with loads of different architectures of a network. It's really useful because you can just build these things really quickly. And then the music sort of processing was done using a library called Music21. So this deals with all sort of the music aspect of it. So for example, like if I want to transpose something, or I want to find out the key of a piece of music, that's all done with Music21. Really expedites the music portion of this, which essentially just allows you to get a lot more done. So one of the key things that's probably the most important thing about machine learning is how you evaluate how good something is, and specifically with neural networks. So essentially you're training and then you're feeding back how good it is, and then you're training through the data again, and you're just trying to continuously improve the network. And the one thing you need to do is you need to be able to say, okay, this is good and this is good for this reason, or this is bad and this isn't working. And the key way to do that during training, Patrick mentioned this, very glad that I don't have to explain this too much, is a loss function. So you need a loss function, and in layman's terms, you've forgotten, a loss function is just how wrong is the network. And it's essentially utilized to correct the weights of the network during the training period. So for example, if the network predicts a probability distribution of what notes it thinks is going to come next, so for example, 50% chance it thinks it should be a C, or like a 20% chance it thinks it should be an A, and then we know that it should be an A, we could say, okay, that was a bit wrong, let's correct that. And then the accuracy is slightly different. It's pretty much the opposite, but a bit different. This is dealing in sort of binary terms. So instead of looking at the probability distribution of notes, it just sees, okay, the network has picked a C as what it's supposed to be, but it's not supposed to be that. So that's not accurate. And it concatenates that over a large data set. So you'll get a accuracy score, hopefully above 50%. And then the third one is on the network side is a confusion matrix. So a confusion matrix is a really useful tool. It's a visualization of which outputs are getting confused with which outputs. So in this context, it will be, okay, the network is predicting these notes, but actually it should be predicting these notes. So it can tell you which notes it's getting confused with, which is a really useful visualization tool. And I'll show you one a bit later. And then obviously the project is not how good are we at predicting the next note of a piece of music, it's can we generate music. So other than just evaluating the network like that, we need to evaluate how good the music generated is. So obviously this is really hard. How do you say if a piece of music is good? How do you say if it fits the grade requirements, other than just looking at is it within the pitch range, for example? So a way of doing this is by doing sort of a frequency analysis of notes between a load of generated music and then the training data. So we can just see how frequently like an A occurs, whatever, or a crotchet occurs, and yeah, just sort of have a visualization of that. And then another method is just me looking at the music and saying, okay, that violates music theory. That shouldn't happen. Why is that happening? And then another method is the same thing, but giving it to my friends to do. So the good thing about this is it's sort of like a blind trial. I can give them some real pieces and give them some generated pieces and get them to pick the ones that they think is the real sight reading music. And that's useful as sort of a final evaluation of the system. So yeah, at this point, I want to mention something that I found really useful. And if there's anything in this lecture that isn't specific to music and not applicable to anyone, it's this part. So data augmentation is a method of increasing your data set without actually sourcing new data. So one of the biggest problems I had was about halfway through my project, the results I was getting were rubbish. And I sort of boiled down the reason to that to be is that I didn't have enough training data. And I wasn't able to source any new training data because they only release a certain amount of sight reading practice music that you can scan in and import, and that takes a lot of time to do. And I didn't want to sort of jeopardize the integrity of the project by just putting in any music, because then it's just going to produce things that aren't suitable for sight reading. So I had a look at data augmentation, and in order to explain this, I'll explain it in a different context. So say, for example, you have a classification network and you're trying to classify images of cats and images of dogs. If you don't have enough of either of them or both of them, and you can't source new images or whatever, you might want to try data augmentation. So an example in this context would be cropping the pictures that you've already got, or rotating them, or flipping them, or just changing them in some way and just copying them each time. So it just increases your data set without actually getting new data, because you're just essentially just expanding the data you've already got. So I sort of had to think of how can I do this with music? And the musicians here will understand this. What I did was I transposed all the sequences of music I had up and down the scale until I just had loads and loads of copies of music. So there are a couple of constraints that needed to be addressed in this. So obviously I don't want to go beyond the maximum pitch that is allowed. I don't want to go below the minimum pitch that's allowed, and I also don't want to introduce keys that are not allowed within that that grade. So obviously I filter out those ones and I just copy the ones that I'm allowed to use. And this tool I wouldn't have been able to achieve any results without this. It increased my data set by a factor of 15, which is insane. So I started with 4,000 sequences of music and ended up with 60,000, which is such a huge improvement. So I was talking about some results. So on the left-hand side, we've got a grid, and this grid represents some of the parameters of the network. So these are things that when you're dealing with neural networks, you want to sort of change different parts of it, like how many layers you have, how many units you have, what optimizer you use, what loss function you use, and loads of other different things, just in order to see which one performs best. And it's not easy to just say, okay, based on what I've done before, I think it's probably going to be that one's right. You do need to try a few different methods. That's just the way things are with neural networks. And in the middle, we've got some of the loss and accuracy. So I didn't train it for 200,000 epochs because that would have taken me years. I trained it for about 60 epochs each time. So an epoch just represents the number of times you iterate over the whole data set during training. And as you can see in the top one, the loss is decreasing. That's a good thing because it represents how wrong the network is, and the accuracy is increasing and sort of plateaus a bit. And on the right-hand side, we've got a confusion matrix. So I mentioned this before, which notes are getting confused with which other notes. So the dark line down the diagonal is really good to see. Essentially, that means it's predicting the correct notes at that frequency. So this is a heat map. So we've got like 60% of the time, 70% of the time, and then a couple of 100%. It's predicting the right note, which is really good. And then there's a couple ones, for example, the A sharp here is being predicted as a B 100% of the time. So that's a bit troubling. But it does sort of indicate that the A sharp is potentially just not very frequent in the training data, which is true because it's a relatively unique note. So it's not too much of an issue that it's not predicting A sharps at all, because they just don't feature very much in the training set. So that's not too bad. So here is some of here's in the top left, we've got actually a piece of music that was generated using the neural network. So this is a bit of grade 5 violin sight reading music, because that was the training data I had. And as you can see, it looks all right, actually. The musicians in the audience will probably see this and think, yeah, that could potentially be a grade 5 violin piece of sight reading music. So this is obviously one of the better ones I'm showing you. And unfortunately, I can't play it for you because of the sound issues. But on the right hand side, we've got all the graphs around the edge. We've got the results of the human testing. So I gave my friends a questionnaire, how good is a piece of music, and a bunch of other things, and asked them to give a response. So in the top right one is probably the most important one. So it's just, is this suitable for grade 5 violin sight reading music? And the left bar represents one seeding method. So the seed is a thing that we put in to sort of start off the generation method. I won't go into that. But in this seeding method, 50% of the time, they said that the pieces were suitable, which is pretty good. That is better than what I was expecting. In the middle one is a control data. So 90% of the time, the real pieces were suitable for grade 5 sight reading. And then on the right hand side, we've got a different seeding method, and that was only 20% were suitable. So after I tried to sort of optimize that as much as possible, I decided to sort of extend it by seeing if I could add any different parts of the music that I hadn't added before. So I was just focusing on pitches and notes, note lengths before, because they're sort of the most important parts of a melody. But what happens if I add slurs or dynamics or other like markings like fingerings or bow markings? What happens then? So I tried a bunch of different network structures, adding loads of features, taking them away to see what I could do. The general takeaway from that is the more features you add, the more confused the network gets and the less good music it produces. But I did manage to produce some decent results when just adding slurring. So for those who don't know, this is a slur. It essentially just means play those few notes as smoothly together. And in the case of a violin, that would be play it all in the same bow movement. So as you can see, the music looks okay again. And in the top right is how we sort of account for the loss with regard to different parts. So I could separate how good the loss is with pitches as slurs, as you can see, and they're decreasing, which is obviously quite good. And in the bottom left, we've got 2 pie charts. Both are different generating methods, but it's the same question as before. Is it suitable for sight reading music? And in this method, people said 75% of the time it was suitable, which is quite good. And in this method, it's 50% was suitable. So obviously that was slightly better than the other results. Perhaps the slurring helped the network slightly. I couldn't tell you, but it was some good news to hear that. So I'll just sort of wrap this up a bit now. A general achievement of the project. You might be a bit confused as what happened in the project because it's quite quick going through this. But I managed to produce a system that's capable of generating melodies that are suitable for grade 5 violin sight reading examinations. Obviously, I couldn't test this on all grades and instruments because that's just way too much data. So I also produced the system that's capable of generating sight reading music given a data set and the constraints. So in the case of the violin sight reading music, I gave it the constraints of the grade and I gave it the data, so loads of pieces of sight reading music to test it on, to train on. And the system is capable of taking in any of these combinations of these inputs, so you could test it with another instrument, for example, another grade. And then I provided some experimentation with adding musical features like slurring and dynamics, which is much further described in my report. So you can have a look at that. It's on GitHub. I've put the link in here. it goes much more into details into the outcome of those if you want to have a look at it. And also all my code is on there on GitHub. Also, yeah, email me if you have any questions about this. But yeah, thank you very much for listening. I hope you enjoyed. I hope I didn't speak too quickly and confuse all of you. But yeah, thank you very much for listening.
And with that, we conclude the second episode of our student speaker series. I just want to say a massive thank you to all our speakers this evening. And it was great to hear all about the different experiences everyone brought. And right now, I think I'm a bit of an expert in neural networks. All the links in all the presentations will be in the description very shortly, as well as the speakers, all the speakers as well, socials of all the speakers as well. If you'd like to keep up with the society, don't forget to subscribe and follow our socials using the handle Warwick Data Science Society on Facebook, Instagram, and LinkedIn. And with that, thank you for watching.